We're excited to announce that our very own podcasting platform, Zencastr, has become a new sponsor to the show. Check out the podcast's discount link in our show notes and stay tuned for why we love using Zen for the podcast.
You're listening to the Archaeology Podcast Network.
Hello and welcome to the Archaeotech Podcast, episode 169. I'm your host, Chris Webster, with my co-host, Paul Zimmerman. Today we talk about using muons to look underground and some data plotting with R. Let's get to it. Welcome to the show, everybody. Paul, how's it going?
It's going okay. We're in the middle of December right now. I've been, breaking my bones, digging up tons of bricks on the CRM gig, enjoying it though. And doing some planning for the upcoming year and, this and that. How about you?
Yeah, we're still in Charlotte, North Carolina. We came here last year for the holiday season, and we're here this year where my in-laws live, my wife's family. And yeah, just crazy busy. My whole entire job situation is changing at the end of this month when one contract ends and a few others begin. And because of that, I've just been socked in trying to finish up some clients because I can't or don't want to hand them off to other people on my team. I just want to finish them and get them done. So, which is one of the reasons why we were totally unprepared and skipped an episode. So it's just neither of us really had any time to do it. So it's a good thing to be too busy, I would say, but better than not busy at all. But we are back at it, and we are going to talk about something super cool that Paul found. And maybe I'll just let you tee it up because I love talking about new technology, especially something, that I've heard of as a thing, but never thought to apply to archaeology, which is one of my favorite things, is taking stuff you never thought could intersect with archaeology and intersecting with archaeology. So Paul, tell us what we're talking about.
What we're talking about is a phys.org article that came by on the news feed a week ago now, called Seeing Deeper with Atmospheric Muons, From Archaeology to Geology. And the article is, it's a phys.org thing, so it's very high level, just kind of, hey, here's this thing that was written about. And, they do give the link to the original Science Direct article. I looked over the Science Direct article. It's a lot of math that's over my head, but it does give some good ideas of things that could be done using muons as an imaging tool. And basically what they are, it's a kind of particle intermediate in weight between an electron and a proton that's generated in cosmic rays in the upper atmosphere. And we're being bombarded with them all the time. They're so small that they tend to pass right through most any kind of object. But for a number of years, people have been making receptors, counters that can capture these things. And so the article is mostly, it's some Italians, Lorenzo Bonecchi, Raffaello D'Alessandro, and Andrea Giamanco.
Nice.
They well, thank you. Grazie. Molte grazie. They're mostly interested in geological applications, but they're thinking ahead. They're thinking that there are a number of other applications, including archaeological applications. And I actually, once I read that phys.org, it reminded me of something else, which I can't remember if you and I discussed briefly or where I saw it, but there was another article from 2017 called Muon Scanning Finds Hidden Chamber in the Great Pyramid of Giza, and that's on the IEEE Spectrum website. And we'll put all these links, of course, in the show notes.
Yep.
And basically, using these muon receptors, a certain group had found what they think is a big void above the Grand Gallery in the Great Pyramid of Giza. I had forgotten about that article. I had forgotten about this possibility of this possible technique, this application of a different kind of receptor to archaeological applications. But seeing this phys.org, it reminded me of it. And I knew that since you want your tricorder that can see through the ground, that this would be something good for Chris.
I think this is honestly, if you were to, obviously a tricorder from Star Trek is a made up device and nobody knows how it works because it's not real, right? Otherwise we would legit have them right now. But I have to imagine that one of the functions of a system, of a thing like that, is it's just got a really awesome detector that's able to not only expel particles in certain ways and then rate the return, but also pick up stuff that's already expelling, like muons. And one of the cool things I like about muons is and other particles like this that come from cosmic rays is you don't need a particle accelerator. You don't need something else. They just, cosmic rays, I'll talk about those in a second, but when they hit the atmosphere, they scatter into their, basically the particles that make up the cosmic rays. And one of those particles happens to be a muon. And it's if I'm not mistaken, it's a particle that's smaller than an atom. They're just so small, and that's why they pass through most things, except some of them get stopped if the density gets right. But back to cosmic rays for a second. Can we just talk about that? Because, using muon detectors to basically detect the muons that are naturally coming through the atmosphere and coming through this Great Pyramid that was built over, 5,000 years ago, 4,000 years ago, something like that. Yeah. I mean,
4,500 years ago.
Yeah, something like that. So they're using a new detector to shoot through a pyramid that's 4,000 to 5,000 years old. And these muons themselves came from one of almost an infinite number of sources, but one of the sources is our own sun. It emits cosmic rays. And if those happen to hit us, it's unlikely they will, given how a sphere works and where we happen to be. But if one of those rays hits us, and they do, then we get those muons. But some of the muons, in fact, most of them probably came from outside our solar system. I saw one source that said there's a black hole somewhere, a well-known supernova, actually, not a black hole, a supernova that expelled just tons of cosmic rays. And it's likely that some are coming from there. But these take thousands of years to get here because they're many, many thousands of light years away. And these things are traveling at the speed of light. So we're using something that's even older than the pyramid to see the inside of an already super old pyramid. And we're doing that with new technology. And wrapping your head around that is just super awesome.
It's kind of cool. And it also, whether you use it for archaeological purposes or not, the fact that we're talking about cosmic rays and, what we always think of in terms of the big sciencey thing with archaeology, or the first big sciencey thing is carbon-14, which starts with, cosmic rays.
Right.
So it reminds us, or reminds me of something else that I've heard of before. And so that's a hook for me. I did think it's interesting that, a lot of the kinds of, we use a number of different kinds of equipment now to see through things, to see into the ground, for example. And those all rely on a transmitter of some kind, whether it's sound waves or electricity or whatever, and another receptor that's capturing the echo or whatever's passing through. In the case of these muon detectors, we're reliant upon, we, as if I'm doing any of this, we're reliant on these cosmic rays that are in the atmosphere that are, pummeling. Well, not exactly pummeling, because they're passing straight through most everything in their way. And the receptor then captures the ones that it can, in a certain patch that are coming at it in a certain direction, which is interesting because it's not a matter of having a transmitter and a receiver. It's just a receiver capturing what's already out there. And like you said, the density is what matters. So the authors of that article are really interested in looking inside volcanoes, in particular Vesuvius, because they want to see if there's another way of predicting when it might blow again.
Because right now, like you said, we're detecting them as they go through. But I mean, you got to read these articles. If you're listening to this, you just got to read these articles, because the way I understand, I want to see if you understand it this way, Paul, before we get too much further into what they're doing with this, because the way I understand this is they're basically putting a receiver on one side that can detect or stop muons. I don't know if it's stopping them, but it's at least detecting their presence. And they're basically looking over, because in some of the images in that phys.org article, they've got these big plates essentially. And from what I can tell, they're like, okay, so over here where we basically have nothing going through, there's an average number of muons per, what unit of space, probably per, I don't know how far spread out they are, but per square centimeter, per square meter, who knows, right? But then you move over here and there's far less or far more muons per square centimeter. So that means if there's far less, something is stopping them. They're being stopped by some dense thing that is able to stop a muon, whereas it's not being stopped in another place. Now, some of them are probably just randomly being stopped by whatever. So you got to take average numbers here. And that's why these detectors are essentially really sensitive, so they can detect those, I would imagine, really small changes in percentage of muons detected. And even a small percentage change in an average area would probably tell you that something is likely either there or not there, depending on what you're trying to figure out.
Yeah, I'm curious to see where this technology goes, because right now it seems to me like the examples that we've got for it are on very, very large objects, like no smaller than the Great Pyramids. But the examples that they give as potential uses in the future or in the near-term future are, for example, scanning the contents of cargo vans, with, I guess, a detector on one side and a detector on the other side, and then seeing what the difference is. Mm-hmm. So hopefully what the authors are proposing is that this kind of technology is going to, like everything else, become faster and more miniaturized as we go along, and be able to be used on smaller at finer grain resolution than what's currently available. And so, yeah, we don't all need to make scans of the Great Pyramid, but it would be cool if it could be used at a smaller scale for investigating the insides of, X, Y, or Z structure. They also give an example of putting the detector down a borehole to, I guess, look for voids in the rock and soil around, I think in the illustration they have, it looks like somebody's yard. That would be an interesting thing. It would be interesting to see if then we could use this as not fully non-invasive, but definitely less invasive than regular excavation method of subsurface perspection, right? Drill a borehole, drop the receptor down there, and see what the densities are like around it. So in that way, I guess maybe it would be somewhat like using, what's the one? I'm trying to blank on the word. The sound waves, when they fire the shotgun shell, basically. At the ground.
Like sonar, basically.
Yeah, the sonar, basically. Yeah, it'll be really interesting to see, because this is another one of those technologies that's not going to be archaeologists driving the bus with it, but definitely there'll be some adaptations coming up soon, I think, that will allow us to use it productively.
Yeah. Well, let's take a break. And then on the other side, we'll talk about some of the uses of this and more applications where it could be beneficial. Back in a minute. Chris Webster here for the Archaeology Podcast Network. We strive for high quality interviews and content so you can find information on any topic in archaeology from around the world. One way we do that is by recording interviews with our hosts and guests located in many parts of the world all at once. We do that through the use of Zencastr. That's Zencastr. Zencastr allows us to record high-quality audio with no stress on the guest. Just send them a link to click on, and that's it. Zencastr does the rest. They even do automatic transcriptions. Check out the link in the show notes for 30% off your first 3 months, or go to zencastr.com and use the code Archaeotech. That's ARCHAEOTECH. Looking to expand your knowledge of X-rays and imaging in the archaeology field? Then check out An Introduction to Paleoradiography, a short online course offering professional training for archaeologists and affiliated disciplines. Created by archaeologist, radiographer, and lecturer James Elliott, the content of this course is based upon his research and teaching experience in higher education. It is approved by the Chartered Institute for Archaeologists as 4 hours of training. That's in the UK, for those of you that don't know. So don't miss out on this exciting opportunity for professional and personal development. For more information on pricing and course structure, visit paleoimaging.com. That's PALEO imaging.com, and look for the link in the show notes to this episode. All right, welcome back to the Archaeotech Podcast, episode 169, and we are talking with Paul. Sorry, that was I had to get it in there. Anyway. So what you were starting to allude to at the end of that last segment was we need to learn more about what the signals tell us, the density of muons, or how they move through different materials, and what that interaction tells us, right? And we've done this before. And we mentioned sonar. I mean, I always go back to, I know it's fiction, but it's based in reality. I always go back to Hunt for Red October when, they get a new signal from something they haven't heard before, and they basically fingerprint it because they hear something, they check the library of sonar images. It's literally a printed image of the sonar return, and it doesn't look like a submarine. It looks like sound waves. And they say, the computer crunches on it, says, does this look like something we've seen before? And it's like fingerprints, right? They can really see it. Well, we do this in archaeology, of course, with ground penetrating radar, with all of our subsurface geophysical non-destructive techniques. We have to study with known sources and say, this is what it looks like when we go through this in these conditions, and then chalk that up in a library. And that's what anybody does that does something like this, even if they're using it for, geology or whatever, looking through volcanoes, whatever the case may be. They have to test this through known things first and see what the thing returns, and then go to a very similar situation and says, does it return the same thing? If it does, then we're on the right track to a signature. And then we can start creating computer programs that say, we shoot it at this thing and it says, oh, it's definitely this because I've seen that 7 million times. And that's what it is. So,
right. Well, that we shoot at is the one caveat there again, because
yeah,
we're not, as opposed to most every other technique we use, we're not shooting these muons. We're just receiving them. So maybe it complicates it again, way over my head. It is a slightly different kind of technique than what we're used to in terms of any kind of non-invasive, imaging.
Yeah. Well, so the other complication would be the atmosphere itself, right? Like it does different conditions in the atmosphere at different times of the year scatter cosmic rays in different ways. And does our position in the solar system as we travel throughout the year cause us to collect varying amounts of cosmic rays, or is it constant as we go around the solar system? Because cosmic rays are coming from outside the solar system, so perhaps it is constant. But what about our own solar system's movement through the galaxy? Does that change how we receive cosmic rays? So there's so many variables there that we have to understand. And I'm sure, I have no doubt that people do understand this. Muons were discovered. I think one of the articles said like it's a little ambiguous. Yeah, but at least the 1930s we knew about it. So we've known about these for a while. Physicists have probably geeked out on these for many, many decades. And I'm sure they know way more than we do. In fact, we have a listener to several of our shows who is an engineer, I believe, at NASA. So maybe he'll chime in and I'll have something to report back. I don't know if he knows
how wrong we got this all.
That's right. So looking forward to that one, because he always tells me something I didn't know, which is pretty awesome. I love learning new things. So, but anyway, there's so many variables involved in this. Like, remember when we talked about the footprints in New Mexico and the carbon sink. The carbon, what was it? The carbon sink effect or whatever it is when reservoir effect, when
reservoir, not sink.
Yeah. When plants are, water-based plants, they absorb more carbon in the atmosphere more carbon dioxide in the atmosphere than other things do, more carbon-14. You get an overinflated estimate of the area compared to things around it. So, but we understand that and we can correct for it. And that's what that means, So I don't know. It's pretty cool. What are some of the uses? Let's talk about that pyramid article a little more and see what they found out of there.
Right. So the pyramid article, like I said before, what they found is a void. And they don't have it. At least this is from 2017. I don't know if they've got better computer models, if they've done more imaging since then. They don't know really the shape of it. They see something roughly the size of the Grand Gallery up above the Grand Gallery. And my understanding is the way that they did this is they used these receptors, muon receptors, both external to the pyramid and internally in different spots in order to try to get something of a 3D picture. But it's just kind of a rough blob of something, less dense somewhere up above the Grand Gallery. One of the, in that article, and again, it's a few years old now, so there may be other details that I haven't gotten. It's just that seeing that phys.org immediately reminded me of this one. Maybe because one of the illustrations on the phys.org article, as well as on the Science Direct article, is a Mayan pyramid being scanned.
Right.
Yeah, but it's very rough. And so one of the criticisms by Zahi Hawass was that, oh no, they're mistaking the signal. It's not a void. There's no real void there. It's not a chamber. What they're seeing is a deliberate construction technique that left voids inside it, inside the pyramid, in order to reduce the weight above, something like the Grand Gallery, which could be true too. The resolution just isn't there yet to know if they're looking at something or if they're just kind of looking at a generalized lesser density, not because of one big void, but because of a lot of little ones that was deliberately part of the construction. In either case, it's really cool, right? If there's a previously undetected gallery kind of void there, that's neat. If you have proof that this is how the building was built in order to keep it lighter on the inside, that is also extremely cool.
Yeah.
And so they're both valid things to explore, and both of them are the result of this scanning technique that didn't exist before.
Yeah, I mean, one thing we can say with certainty is something's different there, right?
Yeah, that's what it seems to be.
You can't deny that. And what I instantly thought, and it might be because of the nature of the graphic on this thing, was maybe it's just the fact that it's not solid rock. It's maybe sand as filler, or something like that, or some other medium. Maybe it's not a void at all, but it's just something less dense than solid rock. I mean, I don't know if they've got it calibrated enough to know that it's truly empty and therefore an intentional or, a construction technique or an intentional chamber, or if it's just less dense than solid rock, therefore it's assumed it's a chamber. I don't really know if they've got that as fine tuned as that.
No, I don't think they do. They certainly didn't in 2017, but it goes back to your analogy from the hunt for Red October. They don't have the fingerprint on it yet. Right?
Yeah, exactly.
They know there's something there, but we don't know what the fingerprint on it is. So they don't know what that something is that they're looking at. Yeah,
and unfortunately, we don't have a lot of pyramids that look like this to be able to, build a library. I mean, there's lots of pyramids around the world, but nobody built them like the Egyptians did, just like nobody really built them like the Mayans did either. I mean, the outside shape is similar, obviously. I mean, as opposed to like step and smooth, but the inside is drastically different, right? And nobody did this like the Egyptians. And I don't know enough about the Great Pyramids at Giza to know if even the insides of all of them look like the Great Pyramid of Giza, right? Do they all have this grand gallery with the air chambers and the other stuff? I don't even know that, to be honest. I'm not an Egyptologist. So, and I know for a fact though,
constructed somewhat differently.
Yeah. Well, they were built so far apart from each other. Yeah.
And they're different sizes and,
yeah, but still super cool. And it would be nice to at least do a scan on the other pyramids and see if they haven't done already. Like you said, this article is about 4 years old now, but it would be cool to see if they've done this in other pyramids yet and to see if they've uncovered similar things or maybe been able to calibrate this against something else. What are some other examples you can think of where we might be able to use this technique?
Well, on pyramidal shaped things, ziggurats. No, I like that example they had of putting the receptor down a borehole, because I really thought that would be useful in a lot of different cases, depending, of course, on the resolution, and also probably dependent on what the materials are, what the building materials are. I would expect that it's probably better used in places that have that use a lot of stone as building materials. So I don't know that it would help me on any of my tell sites where you're looking for mud brick encased in decomposed mud brick, where it's basically all the same material. But I could be wrong. I often am. How about you? Yeah. Do you have, I mean, you don't even have much deposition on most of the places that you work in Nevada. So what kinds of things would it help with you, do you think?
Yeah, I mean, I think it would depend on, and I was trying to scan the Science Direct article for this, and I can't really find it, but I know it's in here somewhere because there's a whole section on the physics of this whole thing. But I'm wondering at what density these are, because that would obviously determine their resolution, right? Yeah. So, how many of these are in a square meter, if that's even a unit of measure you could use for this. And that would really depend on the applications, because if they are traveling through the planet and from what I understand, they can what is it? There's another particle that people try to detect, like the ones that go down into like ice cores down in Antarctica because they need a pure environment. And they interact occasionally and flash on a screen.
Right.
Anyway,
right.
Yeah, I can't remember what that's called, but I wonder, these can pass through solid rock, but can they pass through the entire planet? And what I mean by that is, are they dense enough to where I could build eventually a handheld detector and hold it over the ground and basically see things buried in the ground, like, pottery sherds or projectile points or something like that, because the muons are coming through the planet straight up at me. And you'd think if they were universal enough that they would be coming in all directions, that I would be able to, I guess, electronically filter out ones, or maybe I want ones that are coming at an off angle or a bias from the detector, so I can get more of a 3-dimensional shape on whatever I'm looking at under the ground, and just see if I'd be able to figure that out. But I would like to see it done with a suite of other tools too, right? Because muons are not the only particle that comes through the planet like that. Mm-hmm. And if we built something that could detect other particles and their densities simultaneously and build that whole thing in together as a picture, then man, the applications are just amazing to think of what that could do. And you could basically do it for free, because these things are just bombarding the planet at all times. So I think that would be really cool until we burn off our ozone and there's nothing for those cosmic rays to collide with. And then they just stay cosmic rays and kill us. So until that happens, this would be super cool.
Yeah. Well, since I'm bald, I'm not using any canned hairspray, so I'm not helping with burning off the ozone.
There you go. There you go. Good on you. We should all shave our heads. Do they even make canned hairspray anymore? Man, I don't even think I've seen it. I have no idea.
I'm just like remembering the 80s.
Yeah, exactly. My mom lived on that stuff. Yeah. All right. Well, let's take a break, and we're going to switch gears a little bit and talk about another article that Paul found that is actually open access. You don't see that every day. Back in a minute.
America. We are endowed by our Creator with certain unalienable rights: life, liberty, and the pursuit of happiness. At Grand Canyon University, we believe in equal opportunity, and the American dream starts with purpose. To serve others in ways that promote human flourishing and create a ripple effect of transformation for generations to come. Find your purpose at Grand Canyon University. Private, Christian, affordable. Visit gcu.edu.
O'Reilly. You need parts? O'Reilly Auto Parts has parts. Need them fast? We've got fast. No matter what you need, we have thousands of professional parts people doing their part to make sure you have it. Product availability. Just one part that makes O'Reilly stand apart. The professional parts people. O'Reilly Auto Parts.
Hi, welcome back to the Architect Podcast, episode 160 now. Today, Chris and I are discussing a couple articles that we've read recently and some of the implications of them. We were just discussing muons, and we're going to switch gears here. That previous article was open access, which is great because we could actually read the original article, not just the phys.org news announcement. And this other article is also open access, which, I am a huge proponent of. It makes it so much easier. I get very frustrated when we want to review an article and it's behind a paywall and we have to beg the authors to get us a copy or scrounge copies from other methods. It's an icky feeling about it. Anyhow, this one is also open access. And what it is, it's in the latest issue of Advances in Archaeological Practice. There were actually a lot of very interesting to me articles in this one. I just pulled this one out, not exactly at random, but pretty arbitrarily, just because I thought there'd be something nice to discuss. Maybe not in the context of the article, but more what they've done with what they're discussing. Now, the article itself is called DatPlot, a new R package for the visualization of date ranges in archaeology. And it's by Lisa Steinman and Barbara Vaisova. And basically what this article is, it describes the process that they went through, the logical process, not the programming process, of creating an R package, R being the statistical software that's very popular with a lot of archaeologists.
Yeah, I forgot to give a trigger warning that we were going to talk about R, because you either love it and you understand it, or you have no idea what we're talking about.
Well, R is interesting to me because I absolutely do not love it. I've used it in the past. I get why people love it, but I hate working with it because the syntax is absolutely backwards to me. And that's fine. Everybody doesn't have to use the same kinds of programming languages. Certain things are better for certain purposes. And that goes not just to the tool set, but also to how you think about it. And a lot of archaeologists find R extremely useful and fairly intuitive. I don't find it intuitive at all. And so I'm always bumping up against it rather than being able to use it effectively. Partly that's my lack of familiarity with it. Partly it's because my brain works slightly differently. But I like this article because they're talking about actually solving a very specific problem and building a tool using R in order to solve that problem and the logic behind it. So the problem that they're discussing, and the example they use is our inscribed materials. I'm not even quite sure what the materials are from the territory of Nicaea in northwestern Turkey, what's now Turkey, and looking at it in the Roman period. So they're looking at these inscriptions and the language used in the inscriptions and trying to see patterns of which languages were used in different time periods. And the time periods can be broken down a number of different ways, by century, by quarter century. Certain objects can be tagged to a specific year. And that really piqued my interest. When I was working on my dissertation, I was working in Yemen. We didn't have a very good chronology at the time. We still don't have a great chronology. But so I had a little bar graph that I just assigned to each site, each object, each everything that, it was time periods, and there were like 4 different time periods: Neolithic, pre-Islamic, early Islamic, medieval Islamic, and then a 3-bar scale saying certainly, possibly, or not. So I could get kind of a broad, very rough overview about the duration, the time extents of things. And this is not exactly what they're running into, but what they're running into is a related problem of displaying these times. And how do you interpret and weight the data so that you can show graphically what's happening at various times in history? And so, again, it was through this article, they explained their process and they introduced this package. The fact that the article is open access, the fact that the package is open access, all this was really just, made me happy.
Yeah, one of the things they mentioned in the article I can very much relate to, and everybody can, I'm sure. They talk about the procedure of manually assessing the chronology. And, they're just going through, I think they mentioned at this paragraph I'm looking at, 1,498 inscriptions and checking the binary expressions of the chronology within a relatively long table. I love the the sort of not very committing relatively long table phrase. I imagine the table was incredibly long and just crazy. And they said going through and rechecking this and looking at it and looking at zeros and ones and how they're recording this data, they said the fear of data loss or unwanted changes led to numerous backups of the table, which caused confusion as to which version of the table was even the most recent. I'm just like, everybody's been there.
Been there, done that. And actually, that highlights another thing that I really liked about this. It's a very human, that they're not hiding behind the heavy technical aspects of it. They're saying these are problems that we all can relate to. And so I recommend actually that our listeners read the article, even if they have no interest in Roman archaeology or the specifics of the chronology that they're tackling with this, because it was just nice to see the problems. I was like, oh yes, that reminds me of something. I've bumped up against that exact same issue. The one that really stuck with me is weighting. Yeah. So the example that they use is like, what if you have a pottery type that's in use for 200 years? Do you give it a score of 1 for each of those 200 years? Mm-hmm. Or even if you're broken up by quarter century, do you give it, 4 ticks for each of those centuries? So 8 ticks total. Right. And then you have a coin that's got a specific date that it was minted. Mm-hmm. Well, it only gets 1 tick. Why does the pottery get the 8 ticks and the coin get 1 tick? Isn't one a better tool? So they explain how they weight things, and basically they divide it by the number of possible years that it could have been. So sure. that coin minted in year 1 gets a score of 1 because it was only minted in that 1 year. The pottery that was in use for 200 years gets a score of 1/200th for each of the individual years that you'd want to put it in.
Nice.
Right?
Nice. That's
That
smart.
was just a very smart, very effective, I think, way of dealing with that. But again, it's stuff that I'm always kind of bumping up against conceptualizing. They're tackling it head on here.
Yeah, absolutely. This is really cool. And I have never used R, right? I've seen papers on it. We've had guests talking about it, but I've never actually used it myself. So, I like talking about this kind of thing because the biggest problem, as I've mentioned probably numerous times on this podcast, is not only understanding different technologies, but understanding when you should use different technologies. And that's why I like talking about this actual case study, because somebody might be thinking, oh, that's a really cool thing, but when the heck would I ever use it? And hopefully somebody's listening to this right now, looking at their data table going, yeah, this is absurd. I need to do something else and figure out what this is going to tell me. So I appreciate that what they're talking about, basically, and you've got some experience with this, and we can talk about it.
Well, one of the things they do, I mean, if you do just want to like jump to the very end of the article, dear listeners, their figure 7 shows, 6 and 7, they show they've gone through a number of different transformations and made some educated guesses and give their reasoning for why they smooth things in certain ways and why they divide up the time periods in certain ways. And their last graph shows this curve, a smooth curve that has 3 distinct peaks on it. And then they propose why those peaks might correlate to actual historical events or historical trends, rather, related to Imperial Roman presence and the economic activity. Yeah, you could certainly argue that those aren't the reasons for those peaks. You could even argue that those peaks are fake, that they're caused by all their smoothing of the data, but it does give one a somewhat empirical basis to say, hey, look at these 3 peaks. Maybe we ought to investigate this a little more carefully. Yeah. Does it correlate with other things that we know through other ways, through other means?
Yeah. And that's really cool. And that's what this is all about, right? It's almost like finding a fingerprint, right? And what does that fingerprint of those peaks represent? Does it represent socio-political changes in that area? Does it represent environmental changes that maybe caused different types of, I don't know, pottery or whatever they're talking about to be produced and at different rates or something like that? Is it conquests? I mean, where do you line that up? Where do those peaks line up on a different timeline? And that's really cool. That's a really neat way to look at that.
Since you said fingerprint, that does, and I didn't even realize this until I started talking about it here, but it does line up really nicely with the Muon article because, we don't know if what we're seeing as a lighter density in the pyramid is because there's a chamber there or because it's built differently there.
Yeah.
I mean, exactly. I guess a chamber is built differently, but you know what I mean? If it's a big gap or a bunch of small gaps or different materials or whatnot, we don't know what the cause of those peaks is, but we can have some suppositions and we can explore those. And that's great. And again, because they explain the rationale for why they did everything, both in the specifics of this particular analysis and in the rationale for how they built the tool, the kinds of problems that they were running into that you and I have all run into when dealing with chronology, it makes a lot of sense. It just pulls you right through very, very, very tidily. So I really like that. And I said earlier, though not fully, is that they also have their the project is up on GitHub. So if you want to look at it and modify it and contribute to the project, it's there. And so they opened this tool up for others to use, which I think is absolutely commendable.
Yeah. And the x-axis on that figure 7 is the year, if I'm not mistaken, right?
Yeah.
They don't actually mention that on there. Okay. So that's what I thought. And, that's what's really cool about other like machine learning techniques and stuff like that. Like you could, maybe not machine learning, but definitely supercomputer type stuff where you could toss the results of this into something and say, we know this is true. This is the x-axis. Do you see any other graph or thing where these points line up to something else that's been studied. Maybe there's something in dendrochronology, maybe there's something in carbon-14 dating, maybe there's something in like historical references, like I mentioned, that would line up with this, and just have a computer spit out possibilities for where these peaks would line up. So that's pretty cool. On the Archaeology show, a number of episodes back, we had an article talking about, I think it was on the Archaeology show, talking about a project that was looking at, it was actually a project looking at how climate change has affected the Indian subcontinent basically through time, and how, I think it was something to the effect of how different pottery making techniques ended up having a correlation with massive climatic events. And I'd have to go back and look at the article, but basically it's like on the years where they got more rain, they did less of something else, and they traveled less, or they did something less. And therefore, pottery didn't change much because they learned what they knew. But on years where there was like less rain or something, people learned new things and new techniques, and styles changed because they had more travel and they were able to get around, something along those lines. But who would ever think to look at pottery styles with climate change? Who would think to do that? I'm glad somebody did, but it's just wacky, and we need to collect all these things in one spot. So, the computer super hive mind can say, yeah, that's obviously this. So I don't know. That's the future I want.
Yeah, no, I do too. And, I've said that a bunch of times, that I love being able to compare one set of analysis against another, Yeah. And normally we talk about that with different kinds of receptors. Gee, I really want to see what my magnetic radiometry says versus my resistivity.
Yeah. Exactly.
But absolutely, you can use it in this higher order process like this, and then do it against other kinds of data sets, like you said, historical, things that we know historically.
Mm-hmm. Yeah, for sure.
I don't know if you can necessarily do that numerically with the historical data set, but somebody's working on that. But comparing A to B is really important. And if we can compare A to B to C and start to see patterns emerge, I think that we get a little bit closer to, if not the truth, at least a coherent narrative.
Mm-hmm. Yeah, for sure. Well, that sounds like a good place to end this on. And again, check out the articles in the show notes. We will link to those for sure. There's 3 articles for the muography discussion. And then there's this article about dat plot in Advances in Archaeological Practice. And again, this one's open source because Advances in Archaeological Practice isn't necessarily open source. So there you go. All right. Well, thanks everybody. Thanks, Paul, for finding these. And any last words on this one?
No, I think that we said enough about these, but it's both of these made me happy. So thanks, Chris, for taking the time to talk about them today.
Absolutely. All right. Thanks, everybody. And we'll see you next time.
Bye. Thanks for listening to the Archaeotech podcast. Links to items mentioned on the show are in the show notes at www.archpodnet.com/archaeotech. Contact us at chris@archaeologypodcastnetwork.com and paul@lugal.com. Support the show by becoming a member at archpodnet.com/members. The music is a song called Off-Road and is license free from Apple. Thanks for listening.
This episode was produced by Chris Webster from his RV traveling the United States, Tristan Boyle in Scotland, DigTech LLC, Cultural Media, and the Archaeology Podcast Network, and was edited by Chris Webster.
This has been a presentation of the Archaeology Podcast Network. Visit us on the web for show notes and other podcasts at www.archpodnet.com. Contact us at chris@archaeologypodcastnetwork.com.
Thanks again for listening to this episode and for supporting the Archaeology Podcast Network. If you want these shows to keep going, consider becoming a member for just $7.99 US a month. That's cheaper than a venti quad eggnog latte. Go to archpodnet.com/members for more info.